Chapter 5, The Time Value of Money. In this chapter, we will learn the most important skill in this course, the manipulation of money through time. I would say this is probably one of the most important chapters in this course because almost all formulas, almost all calculations that we will see in later chapters will be based on the sort of the fundamental ideas that you learn here. So let's start with something not related to money. Let's say I gave you a Rubik's Cube. One today, one more in 1 year, and the third one in 2 years. So you can then easily conclude that 2 years from now you have a total of 3 Rubik's Cubes, right? And you can, visualize it on some sort of a timeline where you mark 3 years, today, in 1 year, and in 2 years, and place a Rubik's Cube under each. So after 2 years, you will have a total of 3. Well, money doesn't work this way. You cannot say that if I give you a $100 bill now, the second $100 bill in 1 year, and the third $100 bill in 2 years, then after 3 years, you will have $300. This is wrong. And the difference between money and everything else is that money actually can work for you over time. It can earn interest. Money grows over time. Let me ask you another question. Which one would you rather have? Receiving $100 today or waiting 5 years and receiving $100 then? And the answer should be receiving $100 today. Why? Why is it more valuable? Why do you prefer today rather than in 5 years, even though it is exactly the same amount of money? First, because receiving $100 today is sooner, but you can also explain it differently and say that you would probably do something with this money, such as invest it or deposit in your bank account. And once you do that, which is a smart thing to do rather than keeping money at home in cash, then it will start earning interest. And after 5 years, today's $100 will be a lot larger amount of money with the interest added to it. And similarly, if another option is receiving $100 in even more distant future, like in 6 years, in 7 years, in 20 years, then it becomes even less attractive to you because you have to wait so long. And so the sooner the money is received, the more valuable it is to us today. And this is what we call the time value of money. $1 in hand today is worth more than $1 to be received sometime in the future, regardless of when in the future it would be received. And the more distant that future point of time is, the less it is worth to you today. So in other words, the same amount of money has different value to us depending on when in time it takes place. So back to the three $100 bills. After 2 years, when you have 3 of those, you actually don't have $300. You have more than $300 because until that point of time, the money will be earning interest if you invested it somewhere. Now let's look at the topic of future value. Let's start with the following example. You make a $100 deposit in a bank today. The bank's annual interest rate is 10%. How much money will you have in your account at the end of the first year? In other words, you're asked to calculate the future value of today's $100 after 1 year at the annual interest rate of 10%. You can imagine a timeline where you mark 2 years. Year 0, which is today, and year 1 in the future. So between year 0 and year 1, we have 1 full year, 365 days. You deposit $100 in year 0, you wait 1 year, you earn the interest rate of 10% on your money, and we need to find the future value in 1 year. How do we solve this problem? You deposit $100 today. Money will grow to 100 plus interest, which is the same as $100 plus 10% of $100, which is the same as $100 plus $10, because 10% of $100 is $10. And $100 plus $10 gives you $110. This is the future value of today's $100 in 1 year. Let's think of a slightly more difficult problem. Again, you make a $100 deposit in the bank today. The bank's annual interest rate is 10%. How much money will you have in your account at the end of the second year? In other words, what is the future value of today's $100 after 2 years at the annual interest of 10%? So we have an extra year here. And again, you can imagine a timeline where year 0 is today. When we deposit $100, we wait 2 years, we earn a 10% annual interest rate on our deposit, and we are asked to find the future value in 2 years. So let's start calculating. During the first year, you earn interest on your 100 deposit. So 10% of $100 is $10. Over 2 years, you earn a total interest of $10 times 2 years equals $20. And so future value after 2 years is $100 that you deposit now plus $20 earned in total interest equals $120, right? No, this is actually wrong. Okay, what's going on here? What would be the right way to solve the problem? The correct calculations are as follows. You deposit $100 today in year 0. In year 1, you have $100 plus interest, which equals $100 plus 10% times $100, which equals $100 plus $10 in interest, which gives a total of $110. Then you leave $110 in the bank account. You don't withdraw anything, you don't add anything, you just leave it. We say that money gets reinvested for another year. So 1 more year goes by, that's the second year on our timeline, and what you will have at the end of the second year is $110 that you had at the beginning of the second year, plus interest, where interest is 10% of $110. That gives you $110 plus $11 in interest, and that adds up to $121. So $100 today, $110 in 1 year, that's the future value after 1 year, $121 in 2 years, that's the future value after 2 years. So notice what has happened here. You earned $10 in interest during the first year and $11 in interest during the second year. What is the extra $1? It's actually nothing but 10% interest on the $10 interest amount from the first year. So 10% of $10, which equals $1. And this is also what we call interest on interest. Let's look again at our calculations. Let's look more closely. Year 0, $100. Year 1, $110. Year 2, $121. Year 1, $110. How did we find it? It was found as $100 at the beginning of the first year plus 10% times $100. Mathematically, we can rewrite it. So in order to not repeat $100 twice, we factor it out. So we write it only once, and then we multiply by 1, which is what's left from $100, plus 10%, which is what's left from 10% times the second $100. Then let's look at year 2 result, $121. How did we find that again? We found it by taking $110 at the beginning of the second year and adding 10% to that number. 10% times $110. Again, let's rearrange it. Mathematically, this is the same thing as factoring out 110 because it appears 2 times. We don't want to repeat it. We write it once, 110, and then multiply by 1 plus 10%. But wait a second, what was 110 again? Let's look at year 1 calculations. 110 was nothing but 100 from the very beginning, year 0, multiplied by 1 plus 10%, right? And so basically we are expanding year 2 calculations a little bit by by writing the very original $100 from year 0 multiplied by 1 plus 10% interest rate times 1 plus 10% interest rate one more time. And that can be shortened if we use power 2 for the parenthesis term, 1 plus 10%. Compare the results from year 1 and year 2, where we factored out $100. Don't they look similar? What's the difference? The difference is we have the second power for year 2 future value. Now, can you guess what year 3 future value will look like? That's right. You change the power to 3. Year 4 future value, the power will become 4. Year 5 future value, the power will equal 5, and so on. Now you saw the pattern, and now you can very easily calculate the future value of some given amount of money and interest rate per year for any year in the future. In general, to find the future value in T time periods, we take the initial amount that we start with and multiply it by 1 plus the interest rate for each time period raised to the power T. So why don't we use something simpler like annual rate, number of years? Because even though in this class we will mostly look at something happening every year, sometimes, like in real life, the frequency will be different. For example, monthly. For example, think about credit cards. You need to pay something for your balance every month. Think about home loans, car loans. We make loan payments monthly. What about rents? You pay rent on your apartment once a month. So there are actually a lot of monthly examples in real life. There are also daily and bi-weekly and all sorts of other frequencies. And not saying years, but instead time periods makes this formula more generalized. The initial amount can be called principal or principal amount. And then what it is multiplied by, 1 plus r to the power t, is also known as the future value factor. So essentially, it's like the connecting piece between how much you start with and how much you will have in the future. So you just multiply the initial amount by that number that this whole thing is equal to. That will get you to the future value. There's actually a table at the end of the textbook, table A1, appendix 1, which shows in columns different interest rates in increments of 1%, 1%, 2%, 3%, and so on. I think all the way to roughly 20%. I would need to check. And rows go from 1 to 2, 3, and so on, all the way, I believe, to 20, which indicate the number of time periods. So you can look up that table, find your combination of R and T, and that will give you the future value factor. The table will show you what the future value factor is. And then you can just plug it into the future value formula. But honestly, we can only use these tables maybe at home, maybe in class, but feel free to use at home if you like. But first, they're pretty limited because they don't give you the options with interest rates, between, say, 1% and 2%, like 1.5%. And for this reason, I'm not even using these tables in class, but just so you know, they're there at the end of the book if you want to try. Instead, I will be showing you formulas and the financial calculator. So we are going to look at the financial calculator steps in a couple of minutes. Now, if you're using the formula by hand, then one thing you should be careful about is how you use the interest rate in the formula, the lowercase r. Either in decimals. For example, if the interest rate is 10% per year, you'd put 0.1. Or instead, you can put 10%. Don't forget to press the percent button. But you should not just put 10. It's not gonna work. You will be way, way off. Then another term used when we talk about future value is money getting reinvested at the end of each year. You can also say that this is the interest gets compounded. The process we use in our calculations is called compounding. And the interest rate, which results in earning a larger amount of money in interest with each year, is known as compound interest, or a similar term is interest on interest. Just to review the example we just had, you start with $100. In 1 year, you still have 100, and you now have another $10 on top in interest. Then after 1 more year, you still have 100. You also earn a 10% interest on that, which is $10. And you also had the previous year's $10, and you earn 10% on $10, which is the extra $1. This extra $1 is the interest on interest. And notice how we don't have interest on interest until the second year. In the first year, we earn the first interest. As the name implies, interest on interest is additional dollar amount interest earned on the interest from the previous year. And things get even more complicated if we look further into the future, year 3, year 4, and so on. Now, if you go back to the calculations that I said were wrong, where you take the $10 interest from the first year, multiply it by 2, and say that this is how much total interest you will have by the end of the second year. Could this be correct? Maybe sometimes under any sort of special circumstances? Yes, this could be correct, and this would be called simple interest. What would be a good example? Let's say the first year goes by, you earn your $10, you withdraw it from your bank account and spend it, or whatever you want to do with it. Give it to a friend. So how much do you have left in your bank account. The original $100, no more than that. And now during the second year, it's like you're back to year zero, starting point. You're starting your second year with a total of $100 in your bank account. And you again earn 10% on $100, which is $10. And you withdraw the interest again. Now you're back to $100, and that will be repeated every year. So if every year, as soon as you earn interest, you take it out of your account and do not leave it in the account, then every year you will be going back to the original $100 and earning interest on that. And so every year you will be earning exactly $10 in interest. $10 in year one, another $10 in year two, then in year three, and so on. And in this case, to find the future value with simple interest, you would need to take the principal amount and add that times the interest rate R, which is the interest amount in dollars, multiplied by T, which is how many years worth of interest there will be. And this again can be simplified by factoring out principal and multiplying it by 1 plus R times T. So notice how the future value with simple interest formula is actually similar to the future value with compound interest formula. The only difference is here T is inside the parentheses rather than the power. This figure is from the textbook. It's figure 5.1 on future value simple interest and compound interest. And it again, illustrates what's going on with earned interest in our problem. You start with $100. 1 year later, you still have it plus $10 extra in interest. One more year, the second year goes by, you have earned another $10 on top. So you are at $120. So 2 years worth of simple interest. But you also have one extra dollar. That is interest on interest. In the third year, you earn the simple interest of $10 again, and you earn extra interest on interest from before. So things kind of get a lot more complicated here, but the idea is with each year you earn your simple interest, so it's like you go upstairs, same height steps, $10 each. But you don't just earn that, you also earn an increasing amount of interest on interest. So you can say that compound interest, which is what's going on here with all these future values, equals simple interest plus interest on interest. It's probably intuitive to say that if you add more years to the timeline, then the future value will be higher because there are more years for your money to grow. The second thing you can say is that if you increase the interest rate, then your money will be bringing you a higher interest. So the money will be growing faster if we increase the interest rate. And now time to learn how to use the financial calculator. This is the list that is also in my syllabus. 3 financial calculators which are allowed in FRL 3000 class. Texas Instruments BA2 Plus, or a professional version which allows for more numbers on the display and a couple other features that technically we don't need. 2 Hewlett-Packard 10B, 3 Hewlett-Packard 12C. I strongly recommend you buy the first one, just the simple Texas Instruments BA2 Plus. This is the one I can help you with. This is the one I will be referring to in all my slides. This is the one that the textbook refers to in its chapters. And all solutions manuals again refer to this calculator. What's so special about it is the buttons that don't exist in regular calculators. For example, you see in the third row the buttons labeled as N, I / Y, PV, PMT, FV. Let's go back to our example in which you deposit $100 at 10% annual interest rate for 2 years. How would you calculate the future value? And remember, we got $121, right? Let's see how you would get it in the financial calculator. Let me bring it up right here. Turn the calculator on, then put $100, right? 100. Change it to a negative value. This is how you should enter the deposit amount correctly. So press the plus minus key. Then you want to tell the calculator what this number means. What is it? It's not the number of years, it's not the interest rate, it's the initial dollar amount. Today, at present, or the present value, PV. You press the PV button. Now the display shows PV equals negative 100. Then you want to enter the interest rate, 10% per year. Again, you start with the value, 10. Not in decimals, without the percent button, just 10. 10, and then you want to save it as the interest rate per year, I over Y, interest per year. And the third thing we need is over how many years the money will be earning interest. In our example, that's 2 years. So enter the value first, 2, and then press N, which stands for number of time periods, 2N. We are done with entering the 3 numbers that are given, and there is always 3 to find the future value. And now we want to compute the future value. Compute, CPT key, future value, FV key. Done. Going back to the negative sign that I used to save the $100 deposit amount, if I did not press it, then the only thing that would be different is the display would give me the answer with a negative sign, negative 121. So technically you can just, ignore the minus sign when you get your answer. So it's not really important yet to make sure you change some values to negative ones. But the book kind of, recommends that you learn it this way with the negative sign. Okay, what else is important? The order in which you enter the 3 numbers that are given does not matter. You can put the interest rate first, then the number of years, then the starting amount. It doesn't matter. A couple more things about financial calculators. 3 things. It's highly recommended in finance courses to increase the decimal places and to round to at least 4 decimal places. Round your answers to at least 4. The default in the financial calculator is 2, right? This is the default. That's what you have when you buy a calculator like this. How do you change the decimal places, let's say to 4, which is the minimum recommended? Press second, then format the dot, kind of the decimal place. Decimal equals 2. This is decimal, not December. Decimals is currently set at 2. You want to change it, you want to override this number. You want to change it, let's say, to 4. Just press 4. Now it has overwritten the default decimals of 2. And press enter. Done. Now you can turn the calculator off, back on, and it's now gonna be rounding everything to 4 decimal places. The second thing that the textbook teaches is to try to clear the calculator before doing any new calculations or after you have done some calculations. You press second, FV, future value. By pressing second, you bring up the text in the second row. So let's try again, second, FV. Now everything is cleared, so there is nothing stored like the $100 present value, 10% annual interest rate. Everything is zeros. However, later in this class, you will realize that this is not good enough to clear your calculator's memory. Sometimes it still stores certain numbers for more complicated problems. And so my preference is doing a full reset of the calculator by pressing second, plus minus, which brings up this text in the second row, which is reset, and enter. Now everything is clear. Unfortunately, the decimal places also go down to the default number of 2. So that is a little price you're paying for making sure everything is 100% cleared in your calculator before you start something new. Okay, let's move on. Next example. Your great-great-great-grandfather deposited $10 at 5% interest 300 years ago. By the way, when a problem does not clearly state which time period the interest rate is for, you should always assume it's for 1 year. So 5% interest should be interpreted as 5% annual interest rate. 3 questions. How much is the investment worth today? The second question is, how much would it be worth today with simple interest? And the third question is, how much more is it worth today with compound interest? So you already know from the earlier slides that with compound interest, money grows faster than with simple interest. So how much of a difference does it make over 300 years? Well, we can answer the first question using the financial calculator, right? Or we can try it by hand first if you want. You're actually free to pick any calculation method you like. You can do everything by hand using the formula from the earlier slides, or you can use the table in Appendix 1 to find what these future value factors equal to, or you can use the financial calculator. You can actually also use Excel. There are ways to do it very quickly in Excel. The answer to question 1 is approximately $22.7 million. So that's how much you would have in your account now from $10 deposited at 5% 300 years ago. In the financial calculator, again, 10 would be your present value, what you started with. And you would change it to a negative value so that when you find the answer, the future value, it will be displayed correctly with no negative sign next to it. Then 5 is your interest rate, 5 IY. 300 is the number of years, right? Let me try it in the financial calculator again. So we have the present value of $10. Make it negative, press PV. 5 is the interest rate per year, 5 IY, interest per year. And 300 is the number of years over which the interest was earned. Compute future value. Here is the number that matches what's on the slide. The second question is, Instead, calculate the future value after 300 years with simple interest. Here, the math works a bit differently. How much interest is earned every year? It's always the same amount. It's always 5% of $10, which is 50 cents. We earn 50 cents 300 times, which increases the money in the account by a total of $150. And with the original $10 that was deposited, we are now at 160. Big difference, right? The answer to the third question, the difference between the future value with compound interest and the future value with simple interest, is enormous. 22.7 million versus 160. Big difference. This is what we call the power of compounding. Next question. 8 years from now, you plan to buy a new car. When you graduate from Cal Poly in 3 years, you will deposit $10,000 towards your car purchase into your savings account. If the annual interest rate offered by the bank is 4%, how much money will you have available for the purchase? Well, again, it's a future value problem, right? We need to compute the future value. There is a trick in this problem, and the trick is, what do you use for the number of years? Do you use 8? Do you use 3? Do you use 5? The correct answer is 5. Because what you need to understand is T in the future value formula, or N in the financial calculator, means over how many years the interest is earned. So in this problem, you make the deposit 3 years from today. So the first 3 years don't count. Nothing is happening. There is no money growing. Everything is delayed by 3 years. So between end of year 3 and end of year 8, your money sits in your bank account and earns interest. How many years? 5 years in total. So the answer will be $12,166.50. And again, you can do this in the financial calculator. Make sure you use 5 for your number of years, N. Let me bring up the financial calculator to show you. Let's clear everything. Second, clear time value of money, or what I recommend, full reset. Second, plus minus, enter. Let's increase the decimal places just to practice. Second, format, let's make it 4, overwrite 2, enter, done. We are depositing $10,000, so I put 10,000, I change the sign to negative, and then I hit PV for present value. The money will be growing at 4% per year. I press 4 IY, interest per year. It will be earning interest over 5 years, between the end of year 3 and the end of year 8. I press 5N, and I need to compute the future value. Compute FV. $12,166 and approximately 53 cents. It's actually 5290, like on the slide. Next question. A friend of yours lost in a bet, and so he now owes you $500. He is also offering you to instead pay you back $530 in 1 year. Which one should you accept? You also know that the money that you have stays in your savings account and earns a 7% annual interest per year, in case this information matters. And it does. So how would we solve something like this? Well, let's say you choose option number 1. You choose $500 now. What happens next? You're probably not going to keep it at home in cash. You're going to put it in a bank account. Maybe invest somewhere else. If you put in your bank account at 7% interest, then after 1 year, it will grow to 535, right? And again, you can verify the math in the financial calculator, right? Let's clear everything, second FV, or my preferred way of clearing is a full reset, just to be sure. Second, plus minus, enter. We can increase the decimal places. Let's do that. Second, format. Let's make it 4 and press enter. So you take $500 today. We need to set it as a negative value, plus minus key. Then press PV, which stands for present value. It will earn a 7% interest rate, 7 IY. It will earn it for 1 year, 1N. And now we can compute the future value. Compute CPT key, future value, FV key. $535 exactly. There are no cents. What's our conclusion? You should take 500 today. Why? Because in 1 year it will be 535. If instead you take 530 from your friend in 1 year, that's $5 less. And let's do one more example. Turns out this formula to find the future value can be applied to a lot of other things. It's not just all about money and how it grows due to earned interest. Let's look at these 3 examples side by side. In the first example, your company has 500 employees. Each year, the company hires 1% more. How many employees total in 20 years? Well, if you use the future value formula, then 500 employees is the equivalent of the principal amount. Hiring 1% more is the equivalent of earning a 1% interest on your money. And 20 years is like in the future value formula. It's also years. So if you use the formula, you can either use 1% for the growth rate, or if you're putting the growth rate in decimals, you would need to put 0.01. The answer will be approximately 610. And these are the keys you would press in the financial calculator. Again, in no particular order, you would enter PV, N, and IY. And then at the end, you press compute FV. Second example, let's say you love cats. You currently live in a teeny tiny apartment. You have 2 cats. Let's assume both cats are female and that each year they will be producing a kitten. And each kitten will also be producing a kitten every year starting the first year. So what does it mean? If you have 2 cats now, how many cats will you have total in a year? 4. How many will you have 2 years from today? 8. How many cats will you have 4 years from today? 16. Then 32, then 64, and so on. So the number of cats doubles every year. And the question is, how many cats will you have in your teeny tiny apartment in 20 years? So the number of cats doubling every year is like 100% increase every year. You can use the future value formula and use 100%, or in decimals, that would be 1. That's the equivalent of the interest rate when we work with money. The answer will be not hundreds of cats, not thousands of cats, but a little over 2 million cats. 2,097,152 cats. That's in your teeny tiny apartment. And these are the financial calculator keys. And the last example. In this article here, I read that mm, there was a study done on the price for TVs between 2000 and 2018. And between 2000 and 2018, televisions experienced an average inflation rate of negative 16.45% per year. Negative. So they have been dropping in price. Let's use this information and calculate how much today's $1,000 TV would cost in 20 years. What's the trick in this problem? 16.45% is not an increase per year, but a decrease. It's equivalent to a negative interest rate. Can we do that in our formula or the financial calculator? Yes. Just put the minus sign. In the financial calculator, you would set your IY, interest per year, to a negative value, just like you do with present values. And the answer you will get is $27.47. So a TV that costs now $1,000 will cost less than $27.50 in 20 years. If prices keep falling at the same rate they have been falling since the year 2000. Present value. What is present value? It's essentially the same idea as future value, except everything is backwards. When we talk about the future value, we are given some dollar amount today, and at some annual interest rate, we need to find what the future value will be in, let's say, 5 years. With the present value, everything is backwards. What we know is how much money there will be in the future, let's say in 5 years. And we need to go back and figure out how much we should start with today so that it will grow to that known future amount of money. Let's start with this example. You want to have $100 in your bank account in 1 year. The bank's annual interest rate is 10%. How much money should you deposit in your account today so that you have exactly $100 in a year? In other words, what is the present value of $100 to be received in 1 year at the annual interest of 10%? $100 in 1 year is what is given. What we need to find is the deposit to be made today that would grow to exactly $100. How do we figure out the deposit amount? Let's use the future value calculations that we already know from earlier slides. We can write deposit multiplied by, open parenthesis, 1 plus 0.1, close parenthesis, equals $100. Now we can divide both sides by 1 plus 0.1. That leaves just deposit on the left hand side and $100 divided by 1 plus 0.1 on the right hand side. And then we calculate the deposit amount, which equals $90.91. And now you can actually, verify that this works. Let's turn the calculator on. So we are saying that if we start with $90.91, right? So I put 90.91, make it negative, save it as present value. Then 1 year later, 1n, after growing by 10%, 10 IY, I should get the future value of 100. Let's double check. Compute future value. Yes, it is $100. So everything works. We can say this slide, I think, is kind of important because I want to try to explain different ways what present value means, how you should look at it. Even though it's, the whole present value explanation is just, almost the same thing as the future value except backwards. I often find students getting confused when it comes to the present value, while future value is a lot more straightforward. So present value is $90.91. Future value in 1 year is $100. We can say that $100 in 1 year is worth only $90.91 to you today. We can also say that you are indifferent between, let's say, receiving $90.91 today and instead receiving $100 in 1 year, right? So $100 in 1 year is more money, but there is a 1 year delay. And this trade-off sort of cancels out, this trade-off between receiving more money but having to wait for it kind of, makes $100 in a year equivalent to $90.91 today. You can also say that you're equally happy between receiving $90.91 and instead waiting for 1 year to receive $100 then. The term often used when we talk about present values is discounting. We have discounted $100 by 1 year, right? So we made its value smaller, right? So if you were instead given an equivalent amount of money now, that would be less than $100. The interest rate here can also be called the discount rate. And this whole process of finding how much something from the future is worth today is known as the discounted cash flow valuation, DCF. Let's look at another example, slightly more complicated. You want to have $400 in your bank account in 3 years. The bank's annual interest rate is 10%. How much money should you deposit in your account today so that you have exactly $400 in 3 years? In other words, what is the present value of $400 to be received in 3 years at the annual interest of 10%? So if we knew how much we would need to deposit today, then we could apply the same steps that we learned from the future value slides, where you would take this deposit, you would multiply it by 1 plus the 10% interest rate, so times 1 plus 0.1, then that would get reinvested for another year, and you would multiply that larger number with the first year interest by 1 plus 0.1, and then that would get reinvested again and be multiplied by 1 plus 0.1 to reach $400. So let's use the future value calculations to find the present value. The deposit amount, which is the present value, multiplied by, open parenthesis, 1 plus 0.1, close parenthesis, take to the power 3, equals $400. Our unknown is the deposit amount, the present value. We can rearrange the terms in the first line and write the whole thing as deposit equals $400 divided by 1 plus 0.1 raised to the power 3. And when you do the math, you will get $300.53. This is how much you would deposit now, so that when that grows by 10%, 3 times, it reaches exactly $400. In general, the present value of some amount of money in T time periods should be calculated as the amount in T periods divided by, open parenthesis, 1 plus R, close parenthesis, raised to the power T. This could be rewritten as the amount in T periods multiplied by 1 divided by 1 plus R, the whole thing raised to the power T. And the fraction 1 divided by 1 plus r to the power t is discount factor. It's called the discount factor, or the present value factor, or the present value interest factor, or abbreviated as PVIF for some interest rate r and some time period t. There is a table in the appendix number 2 at the end of the textbook, which gives the value of this discount factor for different combinations of the interest rate r and the number of time periods t. But it's also pretty limited, just like appendix 1 for the future value factor. It's limited in the sense that it doesn't show interest rates that are not whole percentages. For example, 2.5%. It will give you 2%, it will give you 3% values. And it doesn't show you, the full range of interest rates and time periods. So it's maybe only about 20 different interest rates and 20 different time periods. How would we do our last example in the financial calculator? Let me bring it up. Let me turn it on. Let's clear everything. Full reset. Second, plus minus, enter, right? Essentially, we are using the buttons from the third row again, except really simple. We are given the future value and we need to compute the present value. The rest, everything else remains the same. So in no particular order, you enter three numbers: the $400 future value, 3 years, and 10% interest rate. So we can do $400 first. And just like when we were calculating the future value, here we would need to convert the $400 future value to a negative value. And that's only so that when you find your present value, the answer is displayed without any negative sign. So I pressed 400 plus minus to make it negative, FV. Then it's 3 years in the future. We need to discount that back by 3 years. I press 3N. And then the last thing that should be entered is the annual interest rate of 10%. 10 interest per year, IY key. Compute present value. I pressed CPT PV. The answer rounded to 2 decimal places is $300.53, just like on the slide. And I already mentioned that it doesn't matter in which order you enter the three numbers that are known, that should be known. And the future value should again be set to negative, although technically at this point in class, you can just not worry about it. And when you find your present value, the negative sign should be simply ignored. Figure 5.3 from the textbook. Present value of $1 for different periods and rates. There's a lot of stuff going on here. On the horizontal axis, we have time in years. This is how many years in the future our given future value dollar amount is. 1 year in the future, 2 years in the future, and so on, all the way to 10. On the vertical axis, we have the present value of $1. So if it's $1 received in 1 year, then today it's worth less than $1, right? We already know that this is going to be the case. If $1 is going to be received, let's say, in 8 years, then today it's worth even less. And so each line on this graph represents the dropping of, the present value of $1 when $1 is pushed further into the future, right? That's the, the decline that you see in each line. Now, what are all the different lines? They all look similar. What's the difference? Each line has its own interest rate or discount rate. For example, 5%, 10%. Let's compare 5% line and 10% line. The 10% line is below the 5% line, which means that at 10% interest rate, the present value is smaller, right? Intuitively, this makes sense because the higher the interest rate, the less you should start with today so that it reaches some desired amount of money in the future, right? In other words, to summarize the effect of the interest rate on the present value, the higher the interest rate, the lower the present value, right? So you can afford to deposit less money in your bank account because at a higher interest rate, it will be growing faster and eventually reach the desired amount of money at some point of time in the future. So the higher the interest rate, the lower the present value. And the more years in the future our given future value amount is, the more distant our given future dollar amount is, the more distant in the future it is, the lower its present value. Example, you recently had a child. You want to begin saving for the child's college education. You think that she will need $150,000 in 17 years. You feel confident that you can earn 8% per year. How much do you need to invest today? Well, normally in real life, we would be saving money for things like education or maybe retirement or house purchase by setting aside something pretty regularly, not just once. That's what you will learn in chapter 6. Here in chapter 5, it's all about a single cash flow. So in this example, we just set aside one amount of money, just once. It will not be repeated in the future. We set aside $150,000. We wait 17 years. The money grows by 8% per year. How much do you need to invest today? Following the present value formula, we need to take the future value and divide it by 1 plus r with that sum raised to the power t. We plug in the numbers, $150,000 divided by 1 plus 8%, that sum is raised to the power 17. And the answer we get is $40,540.34. I think I may have made a mistake. Example, you recently had a child. You want to begin saving for the child's college education. You think that she will need $150,000 in 17 years. You feel confident that you can earn 8% per year. How much do you need to invest today? In real life, when we are saving for things like education or retirement or house purchase, we set aside money pretty regularly, maybe once a month, once every few months, once a year. In this problem, things are simplified. We are going to set aside just one amount of money, only once. It will not be repeated again. But whatever we set aside today, which is what we need to calculate, that will be earning interest over 17 years, 8% per year, and it has to grow to exactly 150,000. So what is the present value of $150,000? Following the present value formula, we take $150,000 and divide it by 1 plus 8% with the sum raised to the power 17. The answer we get is $40,540.34. In the financial calculator, you would do the following. Let's turn the calculator on. Let's clear everything. Second, plus, minus, enter. So I reset the calculator. Everything is back to all default values. 150,000 is our goal. That's what we want to have in the future at the end of 17 years. That's our future value. We set it to a negative number. We change the sign to minus. Press future value, FV key. Then we enter the rest of the information. The number of years is 17. I press 17N. And the interest rate is 8% per year. I press 8 IY. Compute PV. 40,540.34. That's the answer I showed on my slide. Example. Mike needs $40,000 as a down payment for a house, which he plans to buy 6 years from now. He earns 2.5% on his savings. He can either deposit one lump sum amount today for this purpose, or he can wait 1 year and deposit a lump sum then. If he waits a year, would he need to deposit more than today or less than today? What do you think? Well, after 1 year, there'll be less time left until for the money to grow to 40,000. So probably he would need to deposit more, right, to make up for the lost year, for the lost 1 year worth of interest. So how much more would he need to deposit if he waits a year? Let's do it this way. If he deposits now, how much would that be? Present value. Calculate present value. You take 40,000 that would be needed in 6 years, and you divide it by 1 plus the interest rate of 2.5%, and that sum is raised to the power 6 for 6 years. The answer we get is $34,491.87. In the financial calculator, let me bring it up and put it right here. Let's clear everything. 40,000 is what we need in 6 years. I put 40,000. I change the sign to negative, and I press FV for future value. It will be needed in 6 years, 6N. And the deposit I will be making now will be earning a 2.5% interest every year. 2.5 IY. Compute present value. $34,491.87. Then let's think about how much Mike would need to deposit if he waits a year. It's kind of very similar. The only difference is there is 1 year less, right? So the only thing that changes in the calculations is the number of years. It's no longer 6, it's now 5. And we take $40,000 that will be needed for the house purchase and divide it by 1 plus 2.5% and the sum raised to the power 5. That gives, as expected, a higher deposit that would be required, $35,354.17. Let's verify it in the financial calculator. Turn on 40,000 negative future value. 5 is the right number of years to use, 5N. 2 0.5 is the interest per year, IY. Compute PV, $35,354.17. And now we can answer our question. If we wait a year, we would need to deposit $862.30 more. We could do the calculations differently. We could start with the deposit that we calculated first, if it's made today, and then simply find its future value after 1 year. So we take $34,491.87 and multiply it by, open parenthesis, 1 plus 0.025, close parenthesis. And that would give the same number we had earlier when we directly calculated the deposit if it's made 5 years prior to the house purchase, right? $35,354.17. I would probably say that this is a less intuitive way to calculate next year's deposit, but it's also correct. And in fact, in finance, in problems like what we are doing in chapter 5 and then later in chapter 6, with a bit more stuff going on, there's often going to be not one, but 2 or 3 or even more solutions, perfectly correct solutions. A completely different approach to find the answer to the same problem. More on present values and future values. The formula we used for the future value says take the present value multiplied by 1 plus r with the sum raised to the power t. The formula to find the present value says take the future value and divide it by 1 plus r, the sum raised to the power t. The two formulas are very similar, right? Except for the future value we have a multiplication, for the present value we have a division. Otherwise the terms look very similar. You might even realize that mathematically it's the same thing. You can look at the future value formula and solve for PV in it by taking the future value and dividing by the future value factor. And that gives you the second formula on the slide. So really, we have been talking about one formula so far. It's known as the basic present value equation. So the present value version of it is the basic present value equation. The future value formula uses the future value factor, which is like a connecting link between the present value and the future value. If you instead want to go back from future value to present value, then we can multiply the future value by essentially 1 divided by the future value factor. And 1 divided by the future value factor is the present value factor. So the present value factor is the reciprocal of the future value factor. And it was already explained earlier that each factor has its own table at the end of the textbook, which you're free to use. Feel free to use if you like. In both formulas, R is the rate, interest rate, or discount rate, or rate of return. It all means the same thing. And both formulas assume compound interest, which includes simple interest and interest on interest. Then let's do another brief summary on how different parameters affect the future value and the present value. Time period. For a given interest rate, the longer the time period, the higher the future value, right? And if the money is growing faster, in other words, if the interest rate is higher, then your future value will be growing too. For the present value, everything is exactly backwards. For a given interest rate, the longer the time period, the lower the present value. Essentially, this is saying that if you need to wait longer to get some amount of money, then its value to you drops, for you drops. For a given time period, the higher the interest rate, the lower the present value. You can think of this as saying that if you want to have some amount of money in the future, at a certain point of time in the future, then you can afford to deposit less today if it will be growing faster. Example, you want to have $5,000 in 4 years. For that, you put some amount of money in a special savings account, which pays a high interest of 6% per year. The bank transfers earned interest amounts to depositors every half a year. How much money do you have to deposit today? So the key word in the question is today, which tells you that we are interested in finding the present value, right? So now we are basically we are done with the main part of this chapter. We know what the future value is, we know what the present value is. And now I have a few examples where things are sort of mixed up. You need to figure out what needs to be found. Is it the present value or the future value? Look for a keyword. Read the text carefully and see how the question is phrased. Keywords for present value are, for example, today. How much you need to start with today. So what do you use for the future value? $5,000, which is given. What do you use for the interest rate R and for the number of time periods T in the formula? Well, you're going to use 3% for the interest rate and 8 for the number of time periods. Why don't you use 6% for the rate and 4 for the number of years? Because the bank transfers interest to you every half a year. This means that you wait not 1 year to see more money added to your account in interest, but only half a year, 6 months. And this is important because it actually makes a difference. Because after the first half a year, you have a little bit more. And then the total that you now have with that a little bit more money gets reinvested for another half a year. And so at the end of the full year, you will actually have a little bit more because of the interest on interest than how much you would have had if you had to wait a full year to get your interest. So it actually makes a difference. And to account for that, to do the calculations correctly, we need to reflect that frequency with which the interest is earned. So if the interest rate is 6% per year, then every half a year it's half of 6%. That's where 3% came from. And the money sits in the account and earns interest not 4 times, but 8 times, because it's twice every year. The answer we get is $3,947.05. Again, financial calculator. Where is it? Here. Turn it on. 5,000 is our goal, what we want to have in the future. Make it negative, press FV. We want to have it 4 years in the future, but we cannot put 4N because this way we will tell the calculator that the interest will be earned 4 times, which is wrong. It will be earned 8 times, 8N. Each time the interest is earned, how much is it? That's the real meaning of IY. Each time the interest is earned is half of the annual rate, 3%. So I put 3 IY. And finally, I tell the calculator to compute the present value. Compute PV, $3,947.05. And so it's important to read the question carefully. Read the words. What do the words tell you about how often the interest is earned? If you realize that the interest is earned semi-annually, then you need to use the semi-annual interest rate and the number of half years. If, for example, you realize that the interest is earned monthly, then you need to use the monthly rate, which is 1/12 of the annual rate that is given. And for the number of time periods, you need to convert everything into months. So whatever number of years you're given, multiply it by 12. If everything is daily, then you need to use the daily interest rate, for which you take the annual rate and divide by 365 days in a year. And for the number of time periods, you use days. And so if you're given a few years, you take the number of years and multiply by 365. That will tell you over how many days the daily interest is earned. So be consistent throughout your calculations. Example, your friend deposited $5,000 today at 8.5% interest for 5 years. You would like to have just as much money at the end of the next 5 years as your friend will have. However, you can only earn 7% interest. How much money must you deposit today if you are to have the same amount at the end of the 5th year? A lot of things going on here, right? Do we need to find the present value or the future value? First, let's summarize more visually what's happening. We have two people, your friend and yourself. Your friend deposits $5,000 today. His account pays him 8.5% interest rate per year. He waits 5 years. He will have some amount of money then. You want to have the same exact amount of money in 5 years in your account. The question is, how much should you deposit so that you also get the same future value? However, your bank pays you only a 7% rate. How would you solve a problem like this? You cannot do it in one step. You have to do it in 2 steps. Step 1, what is the future value of your friend? Then that becomes your future value, which you can then use to go back and solve for your required present value. Step 1, how much will your friend have? He will have $7,518.28. And we found that by taking his deposit, $5,000, and multiplying by 1 plus 8.5%, the sum raised to the power 5. And then your friend's future value becomes your future value, and you use it to find your deposit or the present value using the same number of years, 5 years, but a lower interest rate, 7% rather than 8.5%. So you take $7,518.28 and divide it by, open parenthesis, 1 plus 0.07, close parenthesis, power 5. The answer is you would need to deposit $5,360.43. Why does it make sense that you would need to deposit more? Because your money grows slower. You need to compensate for that. You'll compensate for the slower growth with a much larger deposit today. And eventually, you and your friend will be looking at equal future values. Again, let's quickly do this in the financial calculator. Step 1, your friend's future value, which will also be your future value. Your friend's present value, 5,000, negative present value. 5 years later, 5N, at 8.5% interest rate per year, 8.5 IY, what will be your friend's future value? How much will your friend have in his account after 5 years? Compute future value, 7,518.28. And then that becomes your future value. So actually, in this particular problem, we don't need to, clear and then start all over, kind of re-enter this number. You can immediately make it negative and press FV. It will work. 5 years for you, like it was for your friend, 5N. Your rate is smaller, 7%, 7 IY. Compute your present value, $5,360.43. Right? So you would need to start with $360.43 more than your friend to make up for your money growing slower. Next example. What would you rather have? $4,000 in 8 years or $2,000 now? And you keep all your money in your high interest savings account that earns a 10% interest per year. This problem is kind of, it doesn't tell you clearly what you need to calculate. You need to pick, between the present value and the future value. You can solve it 2 different ways. You can either compare future values of the 2 options you're looking at, or you can instead compare their present values. So let's look at the first method. If you take $2,000 today, after 8 years, how much is it going to grow to? And if it's going to grow to more than $4,000, which is your second option, then you should accept $2,000 today. This is how we are going to approach it. So what is the future value of $2,000 after 8 years at 10% interest rate? We use the future value formula. $2,000 multiplied by, open parenthesis, 1 plus 0.1, close parenthesis, power 8. $4,287.18. And of course, you can always use the financial calculator, where you put $2,000 negative for PV, 8 is your N, 10 is your IY, compute FV. Because accepting $2,000 today will result in having more than $4,000 after 8 years. This is the option you should go with, option number 1. Now let's look at an alternative solution. Probably a little bit less intuitive, although does the same trick. You instead compare the present values of the 2 dollar amounts. Kind of the idea that this problem wants to illustrate is that when you have numbers at different points of time and you want to compare them, you should bring them to the same point of time. That's the point. So you cannot compare 2,000 and 4,000. You cannot say, oh, 4,000 is more than 2,000, so it's better. No. That's like apples and oranges. It should be 2 apples or 2 oranges, right? So let's make it all 2 oranges. What's the present value of $4,000? In other words, rather than waiting for 8 years, how much would you be equally happy with if you were given an equivalent of that today? The present value of $4,000 is $4,000 divided by 1 plus 0.1, the sum raised to the power 8. That gives $1,866.03. Same exact conclusion, because an equivalent of receiving $4,000 in 8 years is receiving $1,866.03 today. That's less than instead receiving $2,000 today. And so between the two options, you should prefer option number 1, receiving $2,000 today. And so to summarize, it doesn't matter if you go with the future values being compared or with comparing the present values of the two options. It doesn't matter at all. Either way, you will come to exactly the same conclusion if you do the math right. Probably it's more intuitive to find the future value and then compare it with $4,000 rather than use the present value method, but they're both equally correct. So it's completely up to you. They are equivalent. Now that we are done with future values and present values, what else can we do on this topic? Well, how about we know both the present value and the future value, but and we also know the interest rate. Can we figure out how many years are between the present value and the future value? Yes. Or instead, we know the present value, we know the future value, and we know how many years there are between the present value and the future value. What's the implied interest rate? We can also figure that out. So in this part of the chapter, we are looking at how we would solve for either the interest rate or the number of time periods. Let's start with finding the interest rate. That's R in the formula or IY in the financial calculator. If you use the financial calculator, then you're computing IY, the interest rate. So you are given both present value and future value, and you're also given the number of years that are in between. Essentially, you're using the same buttons, right? PV, FV, and IY, just like before, except now it's the interest rate which is the unknown. What's important when you use the financial calculator? Either the present value or the future value should be negative. It doesn't matter which one. Either one would be fine. And once again, the order in which you enter the present value, the future value, and the number of years doesn't matter as before. If you're interested in, learning the formula to do this whole thing by hand, then we can, for example, start with the future value formula, which equals present value times 1 plus r, the sum raised to the power t. We need to solve for r, right? So first we divide both sides by present value. Then to get rid of the power t, we take what's on the right hand side, future value divided by present value, and raise that fraction by the power 1 over t. And then we are just, we just need to get rid of 1. So r equals fraction future value over present value raised to the power 1 over t, and then we subtract 1 from the result. This formula is actually not in the book. I don't know why, but this is how you would do it by hand. Let's do an example. You're looking at an investment that will pay $1,200 in 5 years if you invest $1,000 today. What is the implied rate of interest? So what are we given? You invest 1,000 today, that's the present value. In 5 years, you will have $1,200. This is the future value. The formula we just learned that allows to calculate the interest rate, if you use it, you will have 1,200 divided by 1,000. Then that is taken to the power 1/5, and then you subtract 1. The answer you find is 3.714%. Financial calculator. Let's see. Turn it on, right? Then we have $1,000 today. Let's make it negative and save as present value. Then we have 5 years over which $1,000 will be earning interest, 5N. And after 5 years, we know that it should reach $1,200. Do not convert 1,200 into negative 1,200 because you only do it for one of your $2 amounts, either the present value or the future value. We already converted the present value to a negative number, so leave the future value as positive, as is. Press FV. Compute IY, 3.71. Here, the decimal places are, we have 2 decimal places, but we could increase it, and this way we would see the answer like on the slide. Example, a friend of yours offers to you to invest your money into his company and promises that your money will double in 6 years. Should you trust him? Is it realistic? Should you or should you not invest money into his company? Okay, what do we need to calculate? It's not very clear, but let's see what would be, you know, a realistic sort of, let's see if money doubling in 6 years implies a realistic growth rate. So what would be realistic? Maybe 10%, maybe 20%, something like that. Anything more than that would be probably called unrealistic. So let's find the interest rate. What do we need? Wait a second. What's our present value? What about our future value? We don't know those. Or maybe we do. Actually, turns out it doesn't matter what you use for present value. Make something up. As long as it's 2 times that for your future value. Kind of cool, right? In the formula, we actually have a ratio, future value divided by present value. And doubling means that this ratio equals 2. So using the formula kind of makes it less complicated. So we have 2 to the power 1/6 and then subtract 1, which gives 12.25%. So this is probably, you know, a very plausible rate of growth of your friend's, you know, profits. So you should probably, you know, help out your friend and invest your money into his company. Financial calculator. Like I said, anything is okay for present value. It could be 1, it could be 100, it could be 20, 1 million, anything at all. Let's say you use 100 for present value. In this case, your future value should be 200, 2 times your present value. Financial calculator. So let me also make something up. What's going to be my present value? Let's make it 333 negative PV. In this case, my future value should be 666. 666. I leave it as is. I'm not changing it to negative because I already did that for the present value. FV. 6 years, right? 6 is my N. compute IY. 12.25%, just like on the slide. Next, what if instead we don't know how many years lie between our given present value and our given future value? So we are given both the present value and the future value, and we know the interest rate at which the money grows every time period. How many years or time periods in general will it take for our present value to grow to the future value that is given? Once again, make sure you change either your present value or your future value to a negative value, not both. If you change both to negative, you will get an error. If you don't change either one, you will also see an error message on the display. And once again, the order in which you enter the three numbers that are given doesn't matter. If you want to know what the formula would look like, you can derive it. For example, if you start with the future value formula, you need to solve for the power t. For that, let's first get rid of PV on the right-hand side. So we have, if you get rid of PV, essentially we are dividing both sides of the future value formula by PV. And after dropping it on the right-hand side, we are left with 1 plus r to the power t. And on the left-hand side, we have future value divided by present value. The power, to get the power, we need to use a natural logarithm function. Every calculator should have this ln button. So the power t will be equal to the natural logarithm of the fraction future value divided by present value, and then the natural logarithm of that fraction is divided by the natural logarithm of the sum 1 plus r. Okay, example. You have just started your undergraduate degree at Cal Poly. You want to buy a used but nice looking Hummer as your graduation gift, and you want to pay no more than $20,000 for it. You currently have $15,000, but you have an opportunity to invest it at 10% per year. How quickly will you need to graduate? The question implies you need to calculate the amount of time. So we are going to be solving for n, the number of time periods. If you use the formula to find the number of time periods, you would need to first calculate the natural logarithm of the fraction future value divided by present value. Then you would need to calculate the natural logarithm of the sum 1 plus r, and then take the first number and divide by the second number. Plugging in 20,000 for future value, 15,000 for present value, and 0.1 for the interest rate r, you get a little bit more than 3 years, 3.02 years. And this means that you can buy yourself a Hummer as soon as in 3 years. So if you graduate in 3 years, you will have just enough money, $20,000 that you need to buy yourself a nice Hummer. Let's do this in the financial calculator. Turn it on. We have $15,000 today. That's present value. Let's leave it as is. Let's not turn it into a negative value and just press PV. And instead, change $20,000 from the future into a negative value. 20,000 negative FV, which is perfectly okay. Remember, it doesn't matter which one of the $2 amounts that are given you are changing to a negative. It could be either the future value or the present value. The third thing we enter is the interest rate, 10% per year. 10 IY. Compute N, 3.02. Example. A startup has been extremely successful and the owners have been increasing the number of employees by 15% every year. Currently, they have 30 people. How soon will the number of employees double? Again, by the way the question is phrased, you should realize that you're asked to calculate time, the amount of time, the number of years. And in the formula, what do we use for future value? Well, if the number of people today is 30, then double that must be 60. So the future value is 60, the present value is 30. The equivalent of the interest rate R is the annual growth in the number of employees, which is 15% or 0.15 in decimals. You plug in these numbers into the formula to compute the number of time periods and you get almost 5 years, 4.96. In the financial calculator, again, in no particular order, you enter 3 numbers which are given. 30 is the current number of employees. Let's make that negative and save as present value. Double that is 60. That's our future value. Leave it as is. Do not make it negative because you did that for present value already. Remember, you only do it for one of the 2 numbers, either the present value or the future value. The growth rate in the number of employees is 15% per year. So press 15 IY. And you need to compute the number of years. Compute N. The answer is 4.96. Actually, there's something in finance known as the rule of 72. It's a quick and easy way to calculate how long it takes for something to double. Let's say in the last problem, the number of employees to double. All you do is take 72 and divide by the rate of growth, R. R should be used not in decimals, without the percent button, just, the interest, the growth rate, the rate that is given. For example, in the previous problem with the number of employees, the rate of growth was 15%. So to use the rule of 72, you take 72 and divide by 15. 72 divided by 15 gives 4.8. See how 4.8 is very close to 4.96 that we got in that problem, which was the correct answer. So we are a little bit off, but pretty close. And this rule of 72 works pretty well for R, the interest rate between 5 and 20%. Anything below 5 or above 20 makes the difference between this, approximate and the correct answers pretty big. Example, you finally decided to buy a house. You currently have $15,000 and your money sits in a high yield 7.5% per year account. You will need to have a 20% down payment, right? In this country, when you buy a house, typically you don't have the money, to pay for the asking price. So you take a loan from a bank, a home loan. Banks typically require that you pay 20% of the house price yourself out of your account. And the bank will lend you the money for the remaining 80% of the house price. So you will need to have a 20% down payment for that house purchase. You want a starter home that will cost about $150,000 in Inland Empire. How long will it be before you have enough money for the down payment? Well, how long will it be implies that we need to find time. So we need to solve for t in the formula or n in the financial calculator. How much would we need to pay for the down payment? It will be 20% of the cost of the starter home that you would be searching for. What's 20% of 150,000? 20% multiplied by $150,000 equals $30,000. $30,000 is how much you will need in the future. That becomes our future value. Today you have $15,000 in your account. So you want the money in your account to grow from today's $15,000 to $30,000 at some point of time in the future. How soon will that be? That's the question. And you know that $15,000 that you have now will be increasing at the rate 7.5% every year. To figure out the number of years that it will take for your money to grow to 30,000, you can use the formula to find the t, which will give you 9.58 years. Or you can use the financial calculator, where 30,000 would be your future value, 15,000 will be your present value, and again, pick which one of these two you will set to negative, and then 7.5 will be your IY, and you'll be computing n, compute n. But in this problem, you might realize that, oh, wait a second, I have 15,000, I will need 30,000. I will need double of what I have now. So I can use the rule of 72. That allows to speed things up and calculate a lot faster how long it will take for your money to double. It's not going to give the most accurate answer, but it will be pretty close. So to use the rule of 72, we take 72 and divide by 7.5. That gives 9.6 years. Approximately 9.6 years, exactly 9.58 years. The two answers are pretty close. Summarize chapter 6. First, we looked at the concept that is known as the time value of money. It says that $1 in hand today is worth more than $1 in the future. In other words, the same amount of money has a different value to you today depending on when that amount of money will occur. So for example, if you're offered $100 now or $100 in 20 years, it's the same amount of money, but you're definitely going to pick $100 today. It's sooner, and you can also turn it into more money if you invest it somewhere. Maybe as simple as putting it in a bank account. And after 20 years, it will have so much in interest on top of it. Then we compared simple interest with compound interest. Simple interest is when the interest is earned only on the original amount that you start with, whereas compound interest has more than that. It also has interest on interest because you every year you earn interest on what you have at the beginning of that year, which is what you had at the beginning of the previous year with interest on top of that. So every year your starting point is higher and higher and higher. And so you earn an increasing dollar amount in interest with each year. That's compound interest. First, we looked at the future value. So if you start with some amount of money today, if you know the rate at which it will be growing, such as interest rate that the bank pays on deposits people make, then you can calculate how much you will have after a specified number of years. With simple interest, the future value equals the present value or the starting amount of money, also known as the principal, multiplied by 1 plus r times t. With compound interest, we don't have t in the parentheses, but we have it as a power outside the parentheses. And we say that money gets compounded. So the interest that's earned in the second case, the dollar amount in interest is increasing with each year. Whereas with simple interest, it's always the same interest amount every year. Then we looked at the present value, which is looking at things backwards. Let's say you know how much you will have in the future, and you want to figure out how much you should start with today, so that after growing by a certain rate every year, it will reach that given future value amount after a given number of years. We actually did not have the simple interest present value formula, although it exists. The book doesn't cover it either, so we are skipping it. We only looked at the more realistic scenario, like what we have in real life, with compound interest. To find the present value, we take the future value and divide it by the sum 1 plus r raised to the power t. And we say that money in the future gets discounted. So the present value of something in the future is always a smaller amount of money than that future amount of money. And then in the last part of the chapter, we looked at how we may be given both the present value and the future value, but instead we want to solve for the interest rate. Of course, the number of years between PV and FV should be also known. Then we looked at how we may be given both the present value and the future value and the interest rate, but instead we need to calculate how many time periods lie between the present value and the future value. And this is where we can apply the rule of 72. So the rule of 72 is just to calculate the amount of time, how long it takes for something to double, for the present value to turn into the future value that's twice the present value. Where do we use the financial calculator? Wherever we are using compound interest. So the financial calculator, the special buttons on it cannot be used for simple interest. Simple interest, and we only had it for the future value with simple interest, is only done by hand using the formula. Here's another way to summarize the chapter. In the financial calculator, we learn how to calculate the future value, calculate the present value, calculate the interest rate, and calculate the amount of time. Essentially, we have been working with 4 special keys: PV, FV, N, and IY. First, we looked at how to compute the future value when the other 3 are given. Then we looked at how to compute the present value when the other 3 are given, and so on. So 3 things must be known. The 4th thing in this list is what you need to solve for. Just a quick note about computing the interest rate or the number of time periods. Because $2 amounts at different points of time are known, the present value and the future value. One of them, and it's up to you which one, but one of them must be set to a negative value. Here I show that the present value is where you change the sign to negative, but it could instead be for the future values.